Hello, welcome to lesson 1 of unit 7. Ready, set, go. So it says sketch the inverse of the function the same set of axes. Finally, identify each function as even, odd, or neither. So if we want to sketch the inverse, remember inverses are symmetric over y equals x. So I'm going to graph that first. Y equals x. Let's show this line of symmetry. Okay, not perfect, but there we go. So we're going to reflect over that line. And you can pick some points if you want, if you find that helpful. Here we're starting on the x-axis in the negative side. So I'm going to start on the y-axis on the negative side, about there. And then as we're growing our x's, as our x's are increasing, so are our y's. So this time, as our y's are increasing, so are our x's. And it helps sometimes to put another point down. That one's a pretty nice one. So that's a y-intercept. So that's going to be an x-intercept for us. So I'm going to do my best to sort of curve this nicely. And if you want, you can always add in a few more just to give yourself some shape here. So that falls about right there. Sorry, I miscounted. Right. There we go. Okay. So I'm just going to kind of curve this until we kind of run out of space there. Okay. And I think I made that a little too steep. I'm going to flatten that out just a little bit. It comes more like there, I would say. Because here, we want to see that same sort of reflection. But that's pretty good. So it says identify the graph as even, odd, or neither. This one would be neither. So neither, because when I reflected over that axis, if it was odd, I would have gotten the same function back, and I didn't. And it even, it's reflected over the y-axis, and we see that that's not the case here. So question 2. Here we go. We're going to sketch the graph of this one. So let's draw on that line of symmetry again. I'm going to actually, let's just use a pre-made line here. So there we go. So there's my line of symmetry for the inverse, or I shouldn't really call it a line of symmetry. So inverse reflects over this. So, okay. Okay, so let's, when we reflect it, it's going to look a lot more like this, but let's change my color. Let's get a few points to make it somewhat accurate, right? So the 0, 0, it's going to continue to go through 0, 0, so that's nice. Here, if we're over this little one small gray mark, we go up 1, 2, 3. So we're going to have that be the opposite, right? So instead of going left 1 and up 3, we're going to go left 3, 1, 2, 1, 2, 3, and up 1. So that point kind of transforms there. Same thing, I can kind of lock onto this one. This is our slope here. We can see, and now I'm not using these actual numbers, I'm just using the tally marks. Our slope is negative. So the slope here is negative 3 over 1 in terms of the little gray mark. So our slope is actually going to be, we're just switching our x and y, so it's going to be 1 over negative 3. So I can go up 1 over 1, 2, 3 again, and that's where that point transforms to, kind of. So I'm going to do that a couple times. So this one, instead of right 1, down 1, 2, 3, I'm going to go right 1, 2, 3, and down 1. And that's enough to connect our points since this is linear. So I'm going to make this nice and big. It's not perfect, but it's pretty good. So there is our inverse. Now it says identify the function as even, odd, or neither. So this function actually is odd. The original function is odd since it is a line. If I were to change the x and the y values, they would balance each other out. So this one would be odd, right? Linear functions are odd. Okay. Question 3, sketch the inverse of the function. Once again, let's put our line of that y equals x line in so I know where I'm reflecting my graph. So there's my line of y equals x. Okay, so let's change color up here. So where it touches this line, that's going to be the same on both. So here I see that we have a positive 1 y-axis, y-intercept. So that's going to move down here and become a positive 1 x-intercept. It's nice to do those intercepts. Here we have 2 and we're up just like about 1. So that time we're going to go, well, this side we don't really have quite a y showing of 2. So it's going to be somewhere up there. And then let's pick something here, right? We're reaching this negative 1, this negative 1x value. So we're going to reach the negative 1y value in about the same space. So that's just about here, it looks like. So now let's plot these. Let's connect. I'm going to do my best to be neat here. So there we go. There is the sketch of the inverse. Identify this original function as even, odd, or neither. This one's neither. If I were to flip it over the x and y axis, I would not get my same graph back. So that one is neither. Question 4. So question 4, let's draw in our line, our y equals x. So here we go. Oh, that's a little off. Oh man, I might have to hand draw it if my screen's not calibrated to my touch well enough. It is not, so sometimes that happens. Let's just hand draw it. So there's a lot that falls really close to that line. So we're going to have very similar looking graph. But notice, so we kind of veer off right here. So that's going to show the same sort of veering off right there. And we're going to sort of ride along this line until we veer off there. So that's a pretty decent sketch of the inverse, I would say. And identify this as odd, as even, odd, or neither. So if we look at this original function, it exists in sort of quadrants 1 and 3. So if I were to flip it over the y-axis and then flip it over the x-axis, it would still exist in those quadrants 1 or 3, which makes it odd. Okay. And I don't think I explained the linear one that way too as well. So same thing, this one exists in quadrants 2 and 4. So if I flipped it over the x-axis and over the y-axis, it would still exist in those quadrants 2 and 4. Whereas this one, for instance, when I flip this over the x-axis, it would no longer exist in quadrants 1 and 2. It would now exist in quadrants 3 or 4, so it would be in totally different quadrants. Okay, so question 5. So here are the graphs of 3 even functions. Can an even function be invertible? So the answer here is just no. No. Or I should say, no. Unless we restrict the domain, but no, even functions are symmetric over the y-axis. So they're always coming up, they're always ending in the same way. They're always having our long-term end behavior as approaching infinity for the function or approaching negative infinity. Never both of those. So I'm never going to have a situation where when I flip it over the x and y axis, it remains in that same quadrant. Once I flip these graphs over the x-axis, they're no longer going to be the same. So they are not invertible, meaning the inverse is also a function there. So they are not invertible. So I should specify too. I mentioned they're no longer the same, but they're no longer functions. That's the key. So when we reflect over they are no longer functions. Okay, let's move down. Oh, justify your answer. So I guess we can kind of take that part that we just wrote and move it down to part B. Right? When we reflect over y equals x, they are no longer functions. Other ways you can phrase this, right? So that's one way one way we can phrase it. We can say they are not one-to-one. 1 to 1. And what I mean by 1-to-1 is that each y value is not unique. So each y value is not unique, right? So it is a function because that's okay. So it is a function, but its inverse is not. The inverse is not. Because for something to be a function, the y values don't have to be unique. The x values have to be unique. But when we take its inverse, we're switching x and y. We're switching the input and output. So if y wasn't unique, if the output wasn't unique for the original function, then when we switch it to an inverse, that means the input's no longer unique. Okay. Question 6. So it says state the period, amplitude, vertical shift, and phase shift of the function shown in the graph, then write the equation. So it tells us to write it using, write the equation of the graph using y equals sine of x. So let's start with our period. So, right, a period is how long it takes to sort of repeat one full cycle. So there we start, we're at the midline and we're increasing, then decreasing. We've made it back to the midline. So that means our period is 2 pi here. Right, so our period is 2 pi. The amplitude, well, here we have a 5, which means we're counting by 1, 2, 3. I'll put a 4 there. -1, -2, -3, -4, -5. So this is definitely our midline. It's the halfway point between our highs and our low. And since we go up 3 from the midline and down 3 from the midline, our amplitude is 3. So the vertical shift, there is none, right? Our midline is y equals 0. Okay, phase shift. Since it wants us to use y equals sine of x, that typically starts at the midline increasing. So midline increasing when x equals 0. And that's what we're doing. So there's none here either. So our equation here is just simply y equals, our amplitude is 3. So 3 sine of x. There's no special period change, so we don't need to input a b value. Question 7. So our period, let's sort of highlight. It looks like, let's go from, this looks like a midline, but even if it's not, we've found where we started and we're repeating, and that was 0 to 2 pi. So our period is still 2 pi. Okay, so our amplitude, well, let's first look at our high point and our low point. So our low point is at -5 and our high point is at -1. Right, so -1 to -5. That's a total distance of 4, which means we have to go 2 up and 2 down. So our amplitude is 2. In vertical shift, we are shifted down 2 from the original midline of y equals 0. So our midline is now at y equals -2. I'll even dot that on there. So there's our new midline. So our phase shift. So for this one, sine graph, right, we're at the midline and we're increasing. So there is no phase shift here. But our equation is going to be changed to y equals 2 sine of x minus 2. And I just realized I miscounted here. We're down 3 here. So 1, 2, yeah, we're down 3. So y equals -3. So that's going to change our midline to -3. Y equals -3 in our equation to y equals 2 sine of x minus 3. Okay, question 8. So this time it wants us to use cosine, y equals cosine of x as our parent function. So let's look for our period. So period, we start at a minimum there, and we come back to a minimum after just pi. So this time pi is different. So that will change our equation a little bit. So let's think of that, right? So that we're happening twice as fast. So remember, we want cosine of bx in the middle of the other. So if we're happening twice as fast, our b value is going to be 2 pi over pi, right? So 2 pi, the original period, 2 pi over pi, since that's how fast we're going. So it's going to be cosine of 2x. So we'll revisit that a little bit when we actually write our equation in this last step. But remember, b equals our period, 2 pi over our period. 2 pi divided by period. And just like period is 2 pi over b. Okay, so amplitude. Well, where minimum is at 0 and our high point is at 2, so the amplitude is 1. In our vertical shift, since that puts our midline at y equals 1, we're up 1. So midline is y equals 1. Phase shift. So we can think of this as a phase shift because we are starting at the minimum, and normally y equals cosine of x. Normally when x is 0, it starts at a maximum value. Start at the maximum value. So I suppose we do have a phase shift. Now, there's so many possible answers here. So many answers. But basically, we want half the period, pi over 2. So we could go left or right, really left or right. Pi over 2 is going to get us to a maximum. It doesn't actually matter which direction we go on this one. And that's partly because these graphs, cosine of y is an even function. If I reflect it over the y-axis, I'm going to get the exact same graph. So let's go for our equation. We have y equals 1 cosine of 2x. Now, because I'm saying there's a phase shift, I'm not going to do just 2x. I'm going to say x. I'll say plus pi over 2. It could be minus pi over 2. So you could actually put plus or minus. And then you can put the plus 1 at the end. But there's lots of equations here. In fact, you could actually do this one without a shift at all, without a phase shift at all, if you reflect it vertically, right? So that would also be so many answers here. So many possible answers for that equation. And if I wanted to even factor out the 2 here, if I wanted to, sorry, not factor out, if I wanted to distribute the 2, I could just make this 2x plus pi, right? So if I don't like that double parentheses, I could distribute my 2 in if I want. So again, there's lots of ways that we could depict this. Okay, question 9. So question 9, let's look at our period. So here we're at 0. We've hit 0, but we need to hit it twice. We're back again after 2 pi. So our period is 2 pi. There's no horizontal stretch or compression there. From the original parent graph, our amplitude, we're up 1 and down 1 from that midline. So we're 1, and there is no vertical shift here. Our y equals 0 is the midline. Phase shift, again, so cosine, this is actually starting where sine would normally start. So since we're dealing with cosine, we want cosine to be the top. We want a quarter of this period. So pi over 2, this time I'm going to specifically say right pi over 2, because this would be one of the maximum, right? Y equals cosine of x, and that point is right pi over 2. But there, you could also say, let's say you could say left, and we could say 3 pi over 2, right? Left 3 pi over 2, because that is another spot where we're at a maximum. So if I were to write this as a cosine equation, my equation would be y equals 1, I don't need to write the 1, cosine of x minus pi over 2. And I would just leave it like that. Again, we can have multiple answers. Y equals cosine of x plus 3 pi over 2 would be another okay answer. And if I wanted to, I could even write this as, and I'll put also, because it does want me to write it as a sine graph. I could actually just write this as y equals sine of x. That is just the graph of y equals sine of x, just as it is. Okay, so question 10. So our period, let's do that first. So here we're at a maximum value, and we're back at a maximum value after 2 pi. So our period is 2 pi. Our amplitude, our high point is 4 and our low point is 4. So our total distance here is 8, right? 4 and 4, right? 4, negative 4. So our amplitude is 4. Our vertical shift is none, right? Our midline is still at y equals 0. So phase shift, since we want a sine graph now, we want to find we're at a midline. So midline up. So midline going up, or increasing, I should say. So midline increasing. So there's a few places I could look right here. Right here we're at the midline going up. Since that's off to the left, I could say it's left pi over 2. I could also say, or right here we're at the midline going up. So I could also say it's right 3 pi over 2. Right, so and I could keep doing that. I could list so many possibilities here. So my equation, if I use left, let's do 4 sine of x. Since I said left, it's going to be plus pi over 2. and then that's it. I don't need anything else. If I use my right 3 pi over 2, then I would say 4 sine of x minus 3 pi over 2. I mean, for these, there's multiple possible answers. Okay, question 11. The cofunction identity states that sine of theta equals cosine of 90 minus theta and sine of 90 minus theta equals cosine of theta. How does this identity relate to the graph in problem number 10? So our axis is in radians. So in problem 10, and it says explain where you see this identity in a right triangle. Let's see if there's any second parts. No, there's not. So in problem 10, we're in radians since we don't see a degree symbol, but 90 degrees is equivalent to pi over 2 radians. So we wanted this to be so problem 10, so the equation for problem 10 for 10 could also be y equals 4 cosine of x with no shift at all, since it's starting on the maximum. So the fact that when we write it as a sine function, we shift it by 1/4 of the period. Right? So when our period is, so if it's 2 pi, 1/4 of 2 pi is pi over 2. And when it's 360, 1/4 of 360 is 90. Right? So that's where we shifted for. And since we want something that's increasing, we're going to do 90 minus pi, so that we are making sure we're sort of backing up to the left so that we are still increasing. If we move to the left, since the left is increasing, we're still going to be increasing, which is why I use the plus pi over 2 to do that increase, to show that we're now kind of addressing the second part of the question. It says, explain where you would see this identity in a right triangle. So in a right triangle, one of the angles is 90. So one of the angles is 90 degrees. That's what identifies as right. And the other two angles, add to 90. We can say that they are complementary. So if one is theta, the other is 90 minus theta, right? So that's going to total 180 degrees if you have that 90 plus theta plus 90 minus theta. Okay, question 12 says describe the relationship between the graphs of f of x, which is the solid, and g of x, which is the dotted. Then write their equations. So describe the relationship between f of x solid and g of x dotted. So for number 12, we see that they certainly look like they have the same period, the same amplitude, the same midline. So those all look the same, but it looks like one is shifted and the other one is not. So let's kind of jot those down. So same period, amplitude, and midline. And if we look, it looks like, so I'm going to outline this solid graph a little bit. So we're back up. So our period is 2 pi. So our equation for the solid graph, y equals, I'll use cosine. And it looks like we're up 3 and down 3 from the midline. So y equals, I don't know why I put y equals. We already have f of x. So 3 cosine of x with no shift at all. And just plus 0 because our midline is at 0. So g of x, we see that we're shifted slightly. Now our graph has dots, so we can see that this is half the period, right? Pi over 2. So it looks like we're shifted. So this looks like it's shifted right. Pi over 4. That quarter of that distance between the maximum and the midline. So our amplitude is still 3. And I'm still going to use cosine. But this time I'm going to do x. Since we're shifted to the right, I'm going to put minus pi over 4. So there is g of x. Okay, question 13. So question 13, if we look at 13, it looks like the things that are the same are the amplitude. Looks like that's the same. And midline are the same. And even the phase shift. Because if we look, they're both starting at maximum here. But this cosine, this first one, so we're starting at 0. We've hit a midline at pi. And we can't even fit a full graph to the right here. We're going to go down this way. And after negative 2 pi, we've hit, so here, negative 2 pi and 2 pi, that whole distance is 4 pi is our period. So our b value is 2 pi divided by 4 pi, or 1/2. So, and it looks like our amplitude is 2 there, right? We're up 2 and down 2. So 2 cosine of x over 2, or 1/2 x. And our midline is at 0, so I don't need to add anything to the end of that. Now, this dotted graph is much faster, right? We're seeing that we've hit a full period after only pi. So here, our period is pi, which means b is 2 pi over pi, or 2. So we're twice as fast in this one instead of twice as slow. So the amplitude is still 2, but now we're going to have a 2x instead of an x over 2 in our parentheses. Okay. Question 14. So here our amplitudes are different. Our amplitudes are definitely not the same. So let's look at our solid graph first. So it looks like our maximum value is 2 and negative 2. So we have an amplitude of 2. And since it's starting at the midline, but it's decreasing, it's midline and decreasing, let's actually just make this a negative 2 to show that we're decreasing. And let's use our sine function. Now let's see, what is our period? So by the time we've gotten half the period, it's pi. So our whole period then is 2 pi. So I'm just going to put an x there. And I don't need a phase shift at all, since I used negative 2 sine of x. I could have written this with a phase shift instead, right? I could have said f of x, f of x equals, I could have said positive 2 sine, and I could have said, okay, I want to shift it really left or right pi. So x, I guess I'll put plus pi, but I could be left or right, plus or minus pi, it doesn't matter. I could have done that as well. I'll put plus or minus, it didn't make a difference there. Okay, so our next graph. So our amplitude is different this time because I see my high value looks like it is 3 and my low value looks like it's negative 3. So the midline's the same, but this time at the midline increasing. So let's use 3 sine. Now let's see if our period is still 2 pi. So we've gone halfway and we're at pi. So yes, our period is 2 pi. So I can just put an x there, and our midline is 0. So for this one, the midline is the same. And phase shift the same. And phase shift are the same. But the amplitude is different. And the direction of the two functions are different. So since I put 2 for here, I'll do this one too. Right, g of x, if I did want this to show a negative sign, I could say negative 3 sine of x, and then I could do plus or minus pi again. So that kind of highlights the differences a little bit more. Okay. Question 15. Describe the relationship between f of x and g of x. So let's start with f of x. We see that they have the same amplitude. So same amp, same period. Let's do midline first. Same midline and same period. Those all look like they're the same. So our high is 2, our low is negative 2. So our amplitude is 2. We could write this as a sine or cosine graph. I'm going to go ahead and try to put my answers depending on what I can kind of see clearly here. So for this graph, our midline is y equals 0. And I see that my maximum and my minimums, they don't really fall at a very clear spot. However, I don't really have any other good key of reference. So that looks about halfway, right? So this maybe looks like it's left pi over 4. It looks like, notice I didn't point this out, but our whole period is 2 pi. So I'm going to say cosine, and I'm going to say left pi over 4. So I'm going to do plus pi over 4. Again, I could have actually used this point right here instead. So I don't need to add anything at the end because my midline is at 0. There's no vertical shift. So for the second one, g of x, my amplitude's the same, so I'm going to go ahead and write 2 cosine. This time I can clearly see that it does fall exactly at that halfway part of pi. So I can see it's plus pi over 2. So different phase shifts there. Okay. Problem 16 says include two full periods, label the scale of your horizontal axis. Do we sketch a graph of the function? Okay, it's like we missed part of it. So this one just gives us a blank grid so we can kind of put our axes wherever, but let's always start with our amplitude, our midline. Those are going to help us identify how far we want to space our y-axis out, and then our period. So amplitude, midline, period. So our amplitude is 3. Since there's nothing added at the end, our midline is y equals 0. So I can make my y-axis just sort of in the middle. Let's add a y-axis in here. That's close enough. Bring that down a little bit. Good enough. And let's say my x-axis, let's put that right about here. We'll show a little bit more. I'll put it right there. So I can show a little bit more on the positive side than the negative. Okay, so that is my amplitude, midline, and my period. Since I don't have any multiplier with my x, my period is just 2 pi. So it means my distance between key points. So distance between, I'm going to say key, in parentheses, key points, is 1/4 times 2 pi, which is pi over 2, because that's almost more helpful when we're graphing than to know the whole period, is to know how far apart are those. So when I say key, I mean max to midline to min back to the midline, and we're going to repeat that cycle. So let's label our x-axis. We need to make sure we fit at least 2 full periods. So let's see, 1, 2, 3. If I count by those, that's only 1 period. So let's count. This is pi, 2 pi. That's going to be a full period. 3 pi, 4 pi. That's going to be 2 full periods. And then another half. And then let's do negative pi, negative 2 pi, negative 3 pi. So we're going to fit plenty in here. We're going to fit much more than we need. You could count every other if you prefer. Okay, and I'm going to count, let's count by twos here. So 2, so let's make that, actually let's count by 1, 2, 3. So up 3, so y equals 3. And let's count 1, 2, 3. I certainly don't need to space it out this much, but why not use the space we have provided? So y equals negative 3, and our midline is at y equals 0. You know what? I think I'm going to change my mind about my x-axis. I don't need this much space, so I'll make that pi over 2. Make this pi, so this is 3 pi over 2. So this becomes 2 pi, and this becomes 5 pi over 2. So pi over 2, this is going to be pi, and this is 3 pi over 2. So we're going to do it that way instead, just to spread it out a little bit more. So let's actually dot these. So here we see that we are positive 3 sine. So at x equals 0, we're going to be at the midline increasing. So I'm going to put at the midline, we're going to increase, and then decrease. So at the midline increasing, then we're going to be decreasing. So there is 1 full period. So here's, okay. So there's 1 full period. And, oh, I just realized I didn't count the same on my left and right side. So it turns out I won't have enough space here. We gotta go back to our original. I apologize for that. I sometimes struggle to count these lines. They move in my brain. Okay, so let's erase these. Okay, and I'm sorry, we're going to backtrack, but that's okay. So we're going to backtrack. We're going to go back to what we had before. Okay, so this is 2 pi. And this is going to be negative 2 pi, and this is going to be negative 3, but we're going to put them in the right spots because that's what I had messed up before. Okay, so here, there we go, that's negative pi, and then here we have negative 2 pi, there we go. So negative 3 pi would be all the way at the end here. Okay, so now we're going to follow that same pattern, only now we're going to be right here, right? So pi over 2, 3, and here we are 3 pi over 2, negative 3. So there is 1 full period. So I'm going to keep that up. Make sure these are curved lines. You don't want to look like a bunch of points here. They are curved. So I'm going to label, so this one is 2.5 pi or 5 pi over 2, 3. And here we have 7 pi over 2, 3. And here we have 9 pi over 2, 3. Okay. So let's go to the left now. So sometimes I like to just place the dots first. Sometimes I connect as I go. It's all a preference. There we go. Always show my arrows to show the graph is continuing. Here we have negative 3 pi over 2, 3. Here we have negative pi over 2, negative 3, and negative 5 pi over 2, negative 3. So there is our graph of question 16. Okay, question 17. So let's start with our amplitude and midline. So amplitude is 2. Midline, again, is y equals 0 because there's nothing added at the end. And our period is still 2 pi since there's nothing connected to that x. So between the max to midline, to min, back to midline, is a distance of pi over 2, horizontal distance for each, just like the last problem we did. So let's put some axes on here. Okay, there's our x-axis, and let's draw a y-axis now. I'll put it more towards the middle, I guess. So there's our y-axis. So let's, I like to always draw my maximum and minimum. A little dotted line, I'll count by, let's look at 1, and let's make this 2, so every other. So our maximum, y equals 2, is that max value. Our midline is y equals 0. And our minimum is y equals negative 2. Again, you don't have to spread yours out so much. I just like to do that so that when I label my points, I have a little bit more room to label. Now we fit tons of periods in that graph above. So let's count by a little bit bigger intervals this time. So let's make this pi over 2, pi, 3 pi over 2, 2 pi, and then 5 pi over 2. So this is going to be negative pi over 2, negative pi, and negative 3 pi over 2. It's going to be exactly sort of 2 periods in there. Okay. So just for a different look, you can keep counting the way we did before as well. So this time minus cosine. So when x equals 0, we're actually going to be at a minimum value. But we're going to shift left pi. So at the minimum, left pi instead of x equals 0. So typically where this is. So let's shift left pi and be at the minimum, right? So left pi, right? Okay, now there's nowhere to go but up from the minimum, and we said our period's 2 pi, so we're gonna go distance of pi over 2 to get to the next sort of key point. So there we go. And here we have one full period drawn. So there's a full period. Let's keep going till we draw at least 2 of them. So, and I'll label these after. there's a second full period drawn. So we fit 2 periods in here. And let's do some labeling. So here we have pi negative 2. Here we have 2 pi positive 2, 0, 2, and negative pi negative 2. And why not, let's label these in between ones, right? Pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, 0. I'm going to make that look like a 5. 5 pi. There we go. Here we have negative pi over 2, 0, and negative 3 pi over 2, 0. Okay, so we have 2 full periods. All right, question 18, it says, name the 2 angles of rotation for theta that have the given trig ratios, and it does specifically give us the range that it's between 0 and 2 pi. So we're going to be working in radians here, since we're using 0 and 2 pi of just one full regular circle. So we're looking at sine of theta equals square root 2 over 2 for question 8. So since sine of theta is positive, right, we're looking for positive y values, right? So positive y values. So positive y, positive y. So those are the 2 places where positive y. And, right, this is the square root 2 over 2. We should really think of that 45, 45, 90 triangle. But since we're in radians, 45 degrees is equivalent to pi over 4. So one of our answers is going to be pi over 4. That's this first quadrant. Now remember that this line right here is pi. So for pi over 4 above pi, our second answer is going to be 3 pi over 4. Question 19. So this time it's cosine of square root 2 over 2. So where cosine is positive is the same as where x is positive. So positive x is in that first quadrant and in the fourth quadrant. So we already figured out that the square root 2 over 2, that's that 45, 45, 90 triangle. So it's not going to change our first angle of pi over 4. That's going to stay the same. And but this one is going to change. We're 2 pi, so we're pi over 4 below 2 pi, or I like to think of it as pi over 4 below 8 pi over 4, which gives us 7 pi over 4. Okay, cosine of theta equals negative 1/2. So this time we want negative cosine, so that's going to be in quadrants 2 and quadrants 3. So negative x. Let me do this a little bit neater. I'm going to do it over here. There we go. So remember, cosine is our adjacent side. So we are thinking of a 30, 60, 90 here. But we have to distinguish between the 30 and the 60 since the 2 side lengths aren't the same. So adjacent, we're saying that the x value, this value right here, is negative 1/2, which would make for this one the y value square root 3 over 2, and for this one the y value negative square root 3 over 2. So if we think about which side is adjacent to this 1/2, or you can think opposite the square root 3, that's our 60-degree angle. So we want a 60-degree angle, or in radians, we're really thinking that's pi over 3. So that's the reference angle. So the pi over 3 reference angle. So remember, this is pi. So for one of them, we're going to say, okay, we have to do pi minus pi over 3, because we're not quite there yet. And here we have to do pi plus pi over 3, because that's how much further we need to go. So instead of using that 60-degree reference angle, pi minus pi over 3, or 3 pi minus 3 pi over 3 minus pi over 3, we get 2 pi over 3 and 4 pi over 3. Right, because this one is 3 pi over 3 plus pi over 3. Okay, so question 21 says sine of theta equals 0. So this is where our y values are 0. So our y values, if I were to draw a little circle here, right, let's just make our radius 1, why not? That means this point here is 1, 0. And this point right here is negative 1, 0. If I made the radius something other than 1, then the point would change as well. If let's say the radius was 2, then the point would be 2, 0 and negative 2, 0. It doesn't matter because when we simplify, when we do that y over r, it comes out to the same value because we have 0 divided by something. So here, since we want between 0 and 2 pi, we're saying 0. And let's see, are we including 2 pi? Yeah, we're including 2 pi, but not 0. So we're not going to use 0 as an answer. We're going to use 2 pi as an answer. And pi. So pi and 2 pi are the two values. If you put 0, you have the correct spot on the coordinate grid. You just didn't look at the interval that it wants us to give our. Okay, question 22. We have sine of theta is negative square root 3 over 2. I'm going to go off to the side a little bit again. So negative sign, that means we're going to be downward, down here. So let's draw our two little triangles, right? Let's finish this. So negative square root 3 over 2 are the y values. Negative square root 3 over 2. So again, we want to think 30, 60, 90, right triangle. And we want to think, okay, what is opposite the square root 3 of 2? Well, that's the 60-degree angle. Now, we already sort of thought about how this converts, right? That's the same thing as pi over 3. So here we're at pi, so we're pi over 3 below pi, so that gives us 4 pi over 3. And my letters are erasing as I write them. And here we're 2 pi, so we're pi over 3 below 2 pi, so let's do 6 pi over 3 minus pi over 3, so and 5 pi over 3. Okay, question 23 now. So question 23 is again using negative square root 3 over 2, but this time with cosine. So cosine is negative in our, let's kind of give ourselves a little more space here, in our second and third quadrants, right? That's where cosine is negative. And since we have cosine of negative square root 3 over 2, that's what this adjacent length is. That's square root 3 over 2, which means this is a positive 1/2 and negative 1/2. You don't have to fill those in. I just find it easier to sort of see them than the x-axis. Well, that makes this angle right here a 30-degree angle, or pi over 6, since we're working in radians. So pi over 6. So remember, we're pi here, or 6 pi over 6 if you want to think of it. So we're pi over 6 above it. So that's going to give us 5 pi over 6. And pi over 6 below. So, and 7 pi over 6. Okay. Question 4, it says, for what angles of rotation does sine of theta equal cosine of theta? Well, there's only two that this happens. So sine of theta equals cosine of theta. We know that when it's a 30, 60, 90, those adjacent and opposite sides, or the x and y is not the same. So the only place that x and y are the same are in our 45, 45, 90 triangles. So we need to think where they're either sort of x and y need to be the same sign. So same sign as well. So there's two quadrants where x and y are the same sign. Quadrant 1 and quadrant 3. So here we want a 45, 45, 90 triangle in quadrant 1. Right, that's going to give us pi over 4. And we want a 45, 45, 90 triangle in quadrant 3. So remember that if this is 4 pi over 4, We want to go pi over 4 more. So it's going to be and 5 pi over 4. So those are going to be the two places where our x and y value are the same for the other 45, 45, 90 triangles, right? 3 pi over 4. For 3 pi over 4, we'd have the sine value positive and cosine negative. And for 7 pi over 4, we'd have a positive cosine value but a negative sine. So they'd have the same absolute value, but they wouldn't have the exact same function. These are the two where the signs, the positive and negative signs, are also equivalent. Okay, and that was our last question. So thank you for watching. Hopefully you found this video helpful.